So far what we have discussed that hydrogen like atom. Now, if it is in external magnetic field, so what will happen? So, when it is in external magnetic field, so we have seen that spectral line which is one line without external magnetic field. So, now under the magnetic field these lines, spectral lines are splitted into different number of lines. Okay. So, we have seen that in case of normal Zeeman effect, where magnetic field is very high. So, magnetic interaction term is very strong compared to LS coupling term. Okay. So, that is the basically condition. So, and there we have seen that each spectral lines means before applying magnetic field, it splitted into 3 lines. It is splitted into 3 lines. So, this it does not matter which spectral line, what is the L value, what is the N value. So, every spectral lines will be split into 3 lines, and that is called generally Lorentz triplet. So, so in this case LS coupling should be very weak compared to the magnetic interaction term, and so we basically neglect this LS coupling interaction, and as I mentioned that magnetic field should be very high, and how much it should be high. So, that is condition is B will be greater than Z to the power 4. So, even Z to the power 4 Tesla. So, even for hydrogen atom Z equal to 1. So, you need greater than 1 Tesla field. So, for second atom helium Z equal to 2, for that Z to the power 4 Z is 2. So, you need basically 8, no, it is Z to the power 4 means 16 Tesla magnetic field. So, 16 Tesla magnetic field in laboratory, it is very difficult to produce, because generally electromagnet in laboratory it can produce maximum 2 to 3 Tesla magnetic field. Okay. And higher than the 2 to 3 Tesla, generally we use superconducting magnet, and using superconducting magnet doing the experiment is also difficult, but anyway. So, even using the superconducting magnet, so field more or less you see generally less than 50 Tesla one can produce. So, generally it is even whatever I know, I have seen in our normal lab. So, magnetic field around 10 to 20 Tesla we are using. So, even 30 Tesla also one can get. So, that is in upper I just considered that okay 50 Tesla. So, that means that for lithium Z equal to 3. So, 3 to the power 4 means 81 Tesla magnetic field. So, hardly we can see using the electromagnet, hardly we can see the normal Zeeman effect in case of hydrogen atom. Using the superconducting magnet, we can maximum we can see the normal Zeeman effect for helium, but other than helium. So, for higher Z this lithium, beryllium etc., we cannot see the normal Zeeman effect, but in our laboratory to demonstrate normal Zeeman effect, generally people use neon and mercury source, okay, neon and mercury atom. So, neon this I think Z value is 10 and mercury Z value is 80. So, now imagine how big, how much field you need. If this is the condition for normal Zeeman effect, that B has to be greater than Z to the power 4. Okay. So, so then we cannot see this normal Zeeman effect for neon and mercury. Then how we are getting this normal Zeeman effect in our laboratory. So, reason is that main reason is that LS coupling has to be very small compared to the magnetic interaction term. So, if either L or S or both or 0 for some atom, then LS coupling term vanish, is 0. Okay. So, whatever the magnetic field, that is really higher than the 0. Okay. So, we will see the normal Zeeman effect. So, that is why for normal Zeeman effect criteria is, we always tell in terms of magnetic field, higher magnetic field, it is not the main criteria. Criteria is always one has to compare with the LS coupling term. So, this magnetic field should be high enough, so that this magnetic interaction term has to be very greater than the LS coupling term. Okay. So, that is the main condition for normal Zeeman effect. So, for next intermediate magnetic field, again we are telling in terms of magnetic field. So, again here main condition is that this LS coupling term and magnetic interaction term, it has to be comparable. Okay. They are closely, although magnetic interaction term has to be, will be higher than the LS coupling term, but they are comparable, their magnitude is comparable. Okay. It is close to each other, there is no very high difference. So, under this condition, whatever the effect of magnetic field on spectral lines we see. So, that effect is called Paschen-Back effect. Okay. And there we have seen that whatever in normal Zeeman effect we see 3 lines, and in Paschen-Back effect, there we see each line is splitted into 2, it is formed the doublet basically, that means they are closely spaced, okay, but they are separable. Okay. So, they form the doublet. So, we will get basically each 3 normal Zeeman splitting or spectral lines will be 3 doublet means we will get the 6 lines. Okay. So, that is the Paschen-Back effect. So, now if magnetic field is very weak, so LS coupling term dominate than the magnetic interaction term, then we have to consider this relativistic correction, then Darwin term, what basically we have to consider the Dirac Hamiltonian. Okay. We cannot neglect this relativistic term and this Darwin term, because they are comparable with the LS coupling term, although they are smaller than the LS coupling term. Okay. So, whenever LS coupling term will be stronger than the magnetic interaction term, so in that case we have seen the magnetic effect on the spectral lines, and that is anomalous Zeeman effect, and we have seen that transition between the P half to S half. So, it is without magnetic field, it is one line, okay, but it is after applying weak magnetic field, it is split into 4 lines. And so, this in case of hydrogen this fine, in case of sodium this line we tell that it is a sodium D1 line. So, sodium D1 line, one can say that it is split into 4 lines, and other P 3 by 2 S half, that transition, it is that line it is in case of sodium it is called D 2 line, and this D 2 line is splitted into 6 lines. Okay. So, in anomalous Zeeman effect the splitting of the lines are more. Okay. So, this is because of strong magnetic strong LS coupling interaction. Now, other now if I apply electric field in place of magnetic field, if I apply electric field, so what happens? So, for that I want to discuss, I will not do much mathematics because this it is not as simple as this Zeeman effect. So, calculation is slightly longer and one need to really need to use more quantum mechanical calculation. So, I will avoid calculation, but I will logically I will try to explain what is the effect of electric field on hydrogen like atom. So, so for hydrogen like atom in electric field, so this effect is called basically Stark effect. Okay. So, what is Stark effect? That is basically the splitting of spectral lines in electric field. It is just like similar to the Zeeman effect or Paschen-Bach effect, okay, in case of magnetic field. So, in case of electric field similar things may happen, and that is called basically star effect. Okay. Now, take electric field and apply it. So, if you take this direction of the electric field like magnetic field in space is along the z direction. Okay. So, electric field is applied along the z direction, okay, and atoms are there. So, now this electric field also is taken, generally electric field is large, it is in general electric field is large, and this electric field is large enough for fine structure to be unimportant. So, what is the meaning of this statement? Meaning of the statement is that in case of Zeeman effect we have seen. So, in atoms this LS coupling term is basically it is responsible for the fine structure, right. So, this has strong influence on the atomic spectral lines. Okay. So, so fine structure here, fine structure to be unimportant means LS coupling term is weak compared to the term of electric field, term related to the electric field. So, electric interaction, magnetic interaction term, and in this case it is electric interaction term that is very strong than the fine structure, means LS interaction term. So, this is the case is similar to the normal Zeeman effect, you know. There we have considered that this magnetic interaction or magnetic field is large enough, so that this magnetic interaction term is very high than the spin orbit interaction term. Okay. So, here also this we have considered this case only. For other case we will not discuss, or other case has no much importance. So, here fine structure is negligible compared to the electric interaction term. So, now Hamiltonian naturally H equal to H 0 unperturbed Hamiltonian plus this perturbed term, in this case it is perturbed term H E dash. Now, as I told this, now this H 0 we can consider this Schrodinger Hamiltonian, right. Because LS coupling term is negligible means this relativistic correction as well as Darwin term they are even smaller. So, they are also negligible. So, here H 0 is nothing but the Schrodinger Hamiltonian. Now, this has been taken as a unperturbed Hamiltonian plus this perturbed Hamiltonian. Okay. So, now perturbed Hamiltonian H E dash due to electric field. So, that is like there we have considered this magnetic moment dot B in case of magnetic interaction term or energy. So, that was minus mu magnetic moment dot B. So, similarly here in case of electric field, electric dipole moment dot, that is D dot E minus D dot E. So, this is similar to this magnetic interaction term. So, D is nothing but the dipole moment. Dipole moment is charge, that two charge separated by a distance. Now, along the z direction we are considering. So, this we have taken that distance z. So, electronic charge E, that is minus charge. So, minus E we have written minus E z. Okay. So, that is the dipole moment of electrons in hydrogen like atom. So, this basically also we see this yeah. So, which electron this dipole moment will depends, it is that electron is where staying, either it is staying at s orbit or p orbit or d orbit. So, that also factor that we will see in calculation. So, in our case this magnetic interaction term, perturbed Hamiltonian, that is equal to ultimately E capital electric field into Z. So, this is the our perturbed Hamiltonian. So, so now we have to consider here that energy unperturbed Hamiltonian, we know the wave function as well we know the energy term. So, energy term is this, and this psi, this suitable eigen function is psi NLM. In case of whatever the from Schrodinger equation, Schrodinger solution, whatever we got the wave function. So, that is the wave function we can use, and now using this wave function we have to find out this perturbed term. Okay. So, expectation value of this Hamiltonian. So, that will give the energy change due to this perturbed term. So, that is we have written here in Dirac notation. So, that one has to calculate this. Now, calculation of this again one has to use quantum mechanics, and it is so basically one has to use this perturbation theory and parity operator. Okay. Using this perturbation theory and parity operator, one can calculate this term perturbed this Hamilton correction term one can calculate. So, I will not calculate this one. So, I will avoid this calculation, but I can logically I can tell you this the effect of this electric field. So, now you see this term. So, here basically this what we have written this one. Okay. So, it will vary, it will depends on this value of this term, it will depend on NLM, right. Okay. So, so this term vanish if n is equal to n dash, L is equal to L dash, and M is equal to M dash. So, here two states. So, this basically transition between two states that gives the spectral lines. No. So, here this what are those states. Okay. So, there N, L, M can be same or can be different. Okay. So, so from this property of this wave function, and as well as I told this wave function is basically the wave function, simultaneous wave function of this parity operator. I have not discussed this parity operator. So, parity operator, so in terms of parity operator, so this operator have the same wave function, simultaneous wave function of psi n L m, So, because this H and H0 and this operator P they commute. Okay. So, that is from hydrogen like atom, it has one can prove it. So, that is why this parity operator also very important for calculating this one. So, here just I am just telling the result if you calculate. So, one can show that this H E dash, this term will vanish if n equal to n dash, L equal to L dash and m equal to m dash. Okay. So, only exists means this will not vanish, only it will exist okay, if or for del L equal to plus minus 1 means L dash should not be same okay, and simultaneously del m equal to 0. Okay. So, when this condition will be satisfied, then this term will exist, and this is nothing but the selection rule. Okay. So, here basically I am telling you the result in terms of selection rule, but if you calculate then basically you can find out the selection rule. Okay. So, after calculation you will be able to show that when del L equal to plus minus 1 and del m equal to 0, only then this transition is possible, otherwise not. Okay. So, and this is nothing but the selection rule. So, avoiding the calculation, I am using the reverse logic, as if this I accepted the selection rule, and applying the selection rule I am telling that this term will exist only when L equal to L dash plus 1 or minus 1 and m equal to m dash. So, simultaneously they have to satisfy this condition, then this term will have some value, otherwise it is 0. If it is 0 means there is the effect of magnetic field on the lines, on the energy levels, right. If it exists only, then we can tell that there is the effect of electric field on the energy levels. Okay. So, now just let us consider simple example that in case of hydrogen atom, so for n equal to 1, so L equal to 0 and m equal to 0. So, sometimes I am writing ml, sometimes I am writing m. So, but both are same. Okay. So, for this energy level, this present one energy level, this present one energy level n equal to 1, L equal to 0, m equal to 0. So, for L n equal to 1, this is the energy level, right. So, now for this, so before applying magnetic field, this is the energy level En, we know this E1 what is the value. Now, if you calculate this one electric field effect, okay, so one has to calculate this. So, this here for this energy level, okay, so this n equal to 1, L equal to 0 and m equal to 0, that means I can write psi 100 E x z psi 100. Okay. So, obviously, here L equal to L dash, m equal to m dash and n equal to n dash. Okay. So, it will as I discussed. So, this term will vanish, this will be 0. Okay. So, here I have, so in this case del L equal to 0. So, that is not allowed. Okay. So, now these lines, there will be, after applying electric field, these lines energy will not change, it will remain same. Now, for n equal to 2, L equal to 0, L equal to 1. So, m equal to L equal to 0, m equal to 0, okay, and L equal to 1, m equal to 0 plus minus 1. So, in this case basically, So, this wave function is for this n equal to 2, L equal to 0 and m equal to 0, psi 2 0 0, and for other case psi 2 n equal to 2, L equal to 1, m is 0, m is plus 1, m is minus 1. Okay. So, basically for n equal to 2 E 2 energy, under this energy there are 4 eigenstate, 4 states, okay, having the same energy. So, basically these are degenerate state. Now, for degenerate state calculating this H expectation value of H is more complicated anyway. So, again I will tell following some logic what is happening. So, if you calculate this term, so if you take same wave function in both place, so 2 0 0, this 2 0 0, so obviously it will be 0. So, if you take individual this one, then for all cases it is 0. Okay. So, there will not be effect of electric field on the energy level. Now, if you take these two, so calculate this expectation value in terms of 2 0 0, this and this one 2 1 0. Okay. So, in this case n is not same, no, n are same fine, but L here 0 and here 1. So, del L equal to plus 1 or minus 1, and m is 0 and m is in this other case also m is 0. So, del m equal to 0. Okay. So, then for these two wave function, then this will not be equal to 0. So, it will give some value, okay, and one can calculate that value. And for taking this one with other these two, you can see that in this case n equal to 1, n are same, n equal to n dash, L this is 0 and this is 1, fine, del L equal to 1 or plus minus 1, it satisfy, but m equal to 0 and m equal to 1. So, del m will be plus or minus 1. Okay. So, so that is not allowed, okay, because only this term will exist when del L equal to plus minus 1 and del m equal to del L equal to plus minus 1 and del m equal to 0. Okay. So, but for these two term or for this and these, okay, it is del L equal to plus 1 or minus 1 whatever, that is fine, but del m equal to it is plus minus 1, it is not 0. So, then this term will vanish. So, only you will have here this combination is allowed, and so here for L equal to 0, m equal to 0. So, this term vanish. So, this originally here you see for L equal to 0, m equal to 0. So, there will be no change of the energy level, but for it is for other. So, degeneracy will be removed for these two state. Okay. So, here basically here this original one, it is for basically, okay. So, here one this term is L equal to 0, m equal to 0, and this term is, this wave function is basically L equal to 1 and m equal to 0. So, m equal to 0, this term is there. So, for other term where m equal to plus minus 1, in that case we have seen that this wave function will vanish, this one will vanish, not wave function, this term will vanish. So, this term originally this because n equal to 2, here 4 states. Okay. So, this for m equal to plus minus and these 2 states, this they remain the degenerate state, its energy will not change. So, basically their wave function is psi 2 1 plus minus 1 as if these 2, and now here we will get only splitted into 2 lines, this and this other one. Okay. So, this one basically for m equal to 0 and other one also m equal to 0. Here these 2 states, this will get basically due to this, for these 2 states is splitted into 2 states, but it is the mixture state. So, that is why wave function for this state is basically comes from these 2 combination of these 2. So, this one can write this wave function for energy, for this energy 1 by root 2 normalized 1 by root 2 psi 2 0 0 minus psi 2 1 0, and other is 1 by root 2 psi 2 0 0 plus psi 2 1 0. So, from the combination of these 2 we will get these 2 states, and they are, so these 2 now non degenerate, and that wave function will get, so we will get 2 energy levels, energy at difference from the original energy, and their wave function is generally in this form. One is, one can show this, one is symmetric, another is antisymmetric kind of wave function for these 2 energy level. So, n equal to 1, n equal to 2, effect of electric field. So, one has to find out n equal to 3, one has to find out, calculate. So, just for these 2 logically I could tell you the splitting of the energy levels due to magnetic, due to electric field, and if we consider the transition. So, one line in this case, as if this, it is splitted into 2 lines. So, for other n equal to 3 you can show that it will be split into more lines. So, there is effect of electric field, due to the electric field there is a splitting of unperturbed energy level, okay, or degenerate energy level. So, degeneracy is lifted, not all, but in some extent. If it lifted also, we could get splitting of into 4 energy levels, but it is split into only 2. Okay. So, partially degeneracy is removed. When degeneracy is removed, so you will get obviously more lines, and that is the, that is called the Stark effect. Okay. So, I could tell you following the logic without calculating in details, because calculation will be it will be difficult for undergraduate student without knowing advanced quantum mechanics. Okay. So, but hopefully I could give you just some flavor of this effect of electric field. So, I think that is what I taught you about the one electron system. So, I have discussed all things, and also for one electron system I have shown you the quantum mechanical, how quantum mechanics is used and get the all information. Although all information we have got from the old quantum, using the old quantum theory, but same things, we same energy expression etc., we got from quantum mechanics calculation, and further some more information also of course we have got. But for spectroscopy, spectral analysis, so we need basically this energy expression and some yeah. So, because transition among these energy levels, so that gives the spectral lines. So, this I have discussed. So, for multi electron system I have I think using the vector model one has to find out the total L, total S, then you will get total J, and then yeah. So, basically whatever for one electron system, whatever the selection rule etcetera, whatever the applicable, for multi electron also all are applicable. So, using the Pauli exclusion principle, using the Hund's rule, so I have shown you how to get the ground state of the atoms, right. So, and from there basically one can find out the spectroscopic term, and if you find out the spectroscopic term, you can basically tell the transition, tell about the spectral lines. Okay. So, I think, and then I have shown you of course, this quantum mechanically what is the I think what is called this Stark effect, what is the Zeeman effect, what is the Feshbach effect, and what is the lamp shift. Okay. So, without details calculation I try to explain, okay, and you will understand more when you will know more about quantum mechanics. So, I think for undergraduate student, if you so far whatever I taught about the atomic physics, so that should be enough. So, from next class onwards, I will teach basically molecular physics, physics of molecules. So, physics of atoms, I think we have covered most of the things whatever required for the undergraduate student. So, I will stop here. Thank you for your attention.